Going to continue on here with chapter 8 and gases. So last time we got into a number of gas laws. So a couple of reminders in terms of units. Very common units are atmospheres, millimeters of mercury, and torr, where a millimeter of mercury and a torr are basically equal to each other. It's a one-to-one relationship between those two. And as we talked about last time, the 760 obviously is an important number. It is our conversion factor to go from millimeters of mercury or torr to atmospheres and back. So again, if you do have atmospheres and want millimeters of mercury or torr, then you're going to multiply by the 760. And if you want atmospheres and you got millimeters of mercury or torr, you will divide by the 760. We talked about several types of gas laws. We talked about Boyle's law. Boyle's law is our P1 V1 is equal to P2 V2 at constant temperature. And basically pressure goes up, volume goes down, and pressure goes down, volume goes up is sort of the relationship that we see there. We also saw sort of Charles' law here, which is V1 over T1 is equal to V2 over T2. And sort of one that's related to it, P1 over T1 is equal to P2 over T2, sort of Guy-Lussac's law. And in this case, and pretty much all cases, the temperature does need to be in Kelvin when we use pretty much any gas law. So even again, as we talked about, if they give it to you in Celsius and they want the answer in Celsius, you still need to go Kelvin into the gas law. This is at constant pressure, obviously this one here. And what we see there is as the volume goes up, the temperature goes up, and the volume goes down, temperature goes down as well. Over here, Guy-Lussac's is constant volume. And again, because of that constant volume, there will be no adjusting of it as the temperature increases. So what we do see actually is the pressure will increase. As the temperature increases, pressure will decrease as the temperature decreases in that particular case. We also saw our friend Avogadro, which is V1 over N1 is equal to V2 over N2, where N here is moles. This is at constant temperature and pressure. So we saw with this one that you can definitely just sort of plug and chug into there. We also saw sort of a consequence of that is with stoichiometry. If you're doing some type of stoichiometry that's involving all gases and it's at constant temperature and pressure, you could do sort of a volume to volume relationship, very much like how we do a mole to mole relationship. And a lot of times that will allow you not to have to use something like the ideal gas law in a stoichiometry problem. It's just sort of a quicker way. You can still use the ideal gas law, but this allows you a little quicker way around it. Putting all those guys together give us the ideal gas law, which is our PV is equal to nRT. And that is, again, the most restricted in terms of units. Pressure has to be atmospheres. Volume has to be liters, moles there for N. T has to be in Kelvin, and R is our gas constant of 0.08206. Or again, you can round it to 0.0821. We also talked that around here about STP. STP is standard temperature and pressure. And that is a temperature of 273, and that is a pressure of 1 atmosphere is what standard temperature and pressure means. That means, again, if you are asked something about STP, you can use those values in the ideal gas law. We saw a relationship that at STP, 1 mole of any gas will equal 22.414 liters. A reminder that that conversion can be used in place of the ideal gas law, but it definitely has to be at STP conditions. If it is not temperature and pressure of 273 or 1 atmosphere, you cannot use that conversion. You do need to use the ideal gas law. The good news is you can use the ideal gas law in any situation, STP conditions, non-STP conditions. You can just plug the numbers in always, and it should come out okay. We finished up with one last. It's good because I'm running out of room on this page here. We have the combined gas law, which is our P1 V1 over T1 is equal to P2 V2 over T2. And this is obviously changes in both pressure, volume, and temperature here. Once again, obviously, temperature, like everyone, does need to be in Kelvin. Any questions on that there? So this one, by the way, is a really good one. It can kind of help you get pretty much any other gas law that you need. For example, we're using the combined gas law. If you remember the combined gas law, pretty much you could get Boyle's, Charles, Guy-Lussac's, all those guys really from it. And the way you do that is essentially whatever is being held constant or whatever you're not given. So for example, if it was constant temperature, you simply would cross out the temperature part, and that is Boyle's law. If you had erasing everything. If you had constant pressure, for example, you would cross out the pressure part, and there's Charles' law right there. Obviously, same thing. If you had constant volume, you could cross out the volume part of it and get yourself back to Guy-Lussac's law. So the combined gas law is a good one. You can remember it, and it will help you get to pretty much all the other formulas. Just take out the thing that's being held constant or the thing that you don't have, and it'll allow you really to pretty much get this one, and this one. So that's not too bad. Any questions on that there? Okay, so continuing on here, the next thing we're going to talk about is how we could calculate the density or the molar mass of a gas. Reminder that density of gases are typically given in units of grams per liter. Density, which is mass over volume, is equal to the pressure times the molar mass divided by the gas constant and the temperature. Really, that and the molar mass down here is the density times the R value, the temperature in Kelvin, and the pressure here. And the density, obviously, once again, would be in grams per liter. Remember, units of molar mass are grams per mole. Now, you could remember these formulas, but truthfully, they are all really based off of PV is equal to nRT. So they're all based off of the ideal gas law, and a way that you can get there by solving for certain things. So, for example, if I solve the ideal gas law for N over V, for example, I would be dividing the RT to the other side. We end up with this. N is moles, right? V is volume, which is liters. That is also the molarity, right? So that is the molarity of the solution. And from that, you could end up with moles per liter, which then you could use something like the molar mass to convert it to grams per liter, which will get you to density. So you could use the ideal gas law to sort of solve it. So these are some formulas. They really are both sort of based off of the ideal gas law. You can use the ideal gas law in these situations if you can't remember these sort of formulas to sort of calculate. So why don't we try one here, and we'll kind of see how it goes. Why don't you first give it a try, and then we'll talk about how you can solve it. A 2.1 liter vessel contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass of the gas? So take a couple minutes, see what you come up with here. And again, molar mass is grams per. Okay, let's take a look. So obviously you could just plug it into that sort of formula we saw on the last page. But again, just in case you cannot remember that formula, we just want to show you again another way you could kind of go by it. So if we pull off the information, we obviously have a volume here that is 2.1 liters. We have a mass there that is 4.65 grams. We have a pressure that is 1 atmosphere. We also have a temperature that's 27 degrees Celsius, and we're looking for the molar mass. So clearly out of the molar mass, which are grams divided by moles or the units, we obviously have the grams part given to us, so we're good to go there. Now, if we think about what we are given here, we can think about the ideal gas law, PV equals nRT. We have a pressure, we have a volume, we have a temperature, and we always have R. That does allow you to solve for moles, which would be sort of the bottom part of what you need. So again, if you can't remember that formula, you could really sort of solve this using the ideal gas law here. And that's what we're going to do. We're going to use the ideal gas law really to solve for moles in this case, which would be N is equal to PV divided by RT. Again, bringing these guys to the other side. Putting our values in here, our pressure, which is 1 atmosphere. Our volume, which is in liters, so it's good to go. Our gas constant. And obviously our temperature here, we do need to convert into Kelvin, so we would add 273 to that, and that's going to give us 300 Kelvin. And that will give us 1 times 2.1 divided by 0.08206 and divided by 300 gives us 0.0853. I guess we'll go. And these are moles, which once again is the bottom part here, what we need. So now we have everything to solve for the molar mass. And that would be our grams, which was given to us 4.65 divided by our moles. I write the right number in there. There we go. And if we take 4.65 divided by 0.08530, going to give us something like 54.5. Again, the units do not cancel, so we end up with grams per mole, which is a molar mass. So as I mentioned before, those two sort of formulas we saw on the previous page really are sort of derived from the ideal gas law. So you could always sort of fall back to the ideal gas law on a calculation of something like molar mass or even density here. Any questions on that there? And again, if we looked at it, that is, pretty much what we got going on here with our RT and our pressure. All right, why don't you try one here? What is the density in grams per liter of oxygen gas at 950 millimeters of mercury and 25 degrees Celsius? And obviously oxygen here is 16 grams per mole. Okay, let's take a look. So in this case, we are looking for density here, and we do have the pressure given to us, which is 950 millimeters of mercury here. We do have the temperature given to us, which is 25 degrees Celsius, which we got to convert anyways, to 98 Kelvin. So once again, you could use that sort of formula that we had in the previous page, but if you cannot remember it, you can again fall back to PV equals nRT. In this case, we have pressure and temperature given to us. We always have R. So in this case, we would want to solve for N over V, which, as I mentioned before, is moles per liter. That is good because moles per liter is pretty close to what we need. And we just need to then do a conversion between moles to grams using the molar mass to get us there, basically. So solving for N over V would give us, these guys are going to go this way, and V is going to come that way. And that will give us P over RT. And we would want to, again, use the correct units for everything. So we do need to convert our millimeters of mercury into torr. So we're going to take out 950 basically and divide it by 760. And that is going to get us 1.25 atmospheres, which is what we need here. We're going to use our 0.08206 liters atmosphere Kelvin mole, and our temperature at 298 Kelvin. When we do all that there, we end up with 0.05111. The units here, atmospheres will cancel, Kelvin will cancel. When we divide that on the bottom, it then becomes moles per liter, which is the molarity. Once again, that is very close to what we need. what we really need to do is get rid of the moles on top. So that is where the molar mass comes into play. And since it is O2, that would be 32 grams per mole. Moles will cancel, and that will leave us in grams per liter, which will get us not a 7. It will give us, looks like 1.64 grams per liter here. So again, that sort of formula that we saw earlier, really from the ideal gas law. And, that's, again, if we kind of go back and look at it, we're doing density. That is what we just solved for. P over RT is that part of it, times the molar mass is essentially what we just did. Any question on how to calculate molar mass or density here? All right, so next thing we're going to talk about is gas stoichiometry. The good news is gas stoichiometry pretty much is the exact same thing as all other stoichiometry. We also saw earlier there that we can use sort of a volume to volume relationship if we happen to be at constant temperature and pressure. But other than that, we would follow our normal sort of steps. If it's a basic stoichiometry, which it probably is, again, we want to make sure we have a balanced equation. We want to convert to moles. We want to do our mole to mole relationship, and then obviously go from moles to some other unit like normal. The main difference in sort of gas stoichiometry problem is somewhere along the way, you basically use the ideal gas law is usually what happens. So somewhere there along the way to use it. A lot of times you will use it at the end and solve for something like volume. If you do use the ideal gas law early on, you would be solving for moles. So those are really the two places where you would sort of use the ideal gas law. And again, if you kind of use it up front, it's usually you would be solving for moles. So you could do the mole to mole relationship. And if you use it on the back end, you're usually solving for volume is a very typical way of doing that. So if we look at this problem here, we want to know what is the volume of CO2 gas. My arrow got a little crazy here, so we'll just box CO2. What is the volume of CO2 gas at 37 degrees Celsius in 1 atmosphere? So if we think about sort of the gas part of it, we have a pressure that is 1 atmosphere for the CO2. We're looking for the volume. We have the temperature, which is 37 degrees Celsius. And we have 5.6 grams of glucose, which is this guy here. So if we think about the ideal gas law here for the CO2, P equals nRT, we have pressure, we're looking for volume, we have the temperature, we have R. So here we are missing the moles to allow us to use it. And that's where the stoichiometry part comes into play. We would use stoichiometry using the 5.6 grams of glucose, as that's the only other number we pretty much have. So we would start like normal. The equation is balanced. We would then take the 5.6 grams of our glucose and we would convert it into moles. And we would get the molar mass from the periodic table. That is 6 times 12.01 for the carbon, plus 12 times 1.008 for the hydrogen, plus 6 times 16 for the oxygen. Looks like 180.2 grams per mole. And if we do that, 5.6 divided by 180.2 gives us 0.0311 moles of C6H12O6. Any questions so far here? Once again, we're really kind of missing the moles for the CO2. So this is the stoichiometry part. So the relationship between the glucose and the CO2, as we see from the equation, is for every 1 mole of our glucose, we get 6 moles of our CO2. So this is really the third step here. We'll take our moles of our glucose. We will use stoichiometry to figure out how many moles of CO2 that would be. So 6 moles of CO2 up on top, 1 mole of our glucose on the bottom. So we're going to take that times it by 6. It's going to give us 0.18646 moles of CO2. That is the last thing that we were missing here from the ideal gas law. So now that we've got to CO2, this is again where we will actually use the ideal gas law. In this case, we're interested in volume. So volume would equal nRT divided by P. And all this is for CO2, obviously, at this point. Putting in our moles that we just calculated using stoichiometry, 0.18646. Using our gas constant there. And our temperature, which we do obviously need to convert into Kelvin. So that's 37 plus a 273 is 310 Kelvin. All divided by our pressure, which is already an atmosphere. So we're good on that, which would be 1. So in this particular case, we will end up with, looks like, 4.74 liters of CO2 in this case. So again, a lot of times gas stoichiometry is pretty much like all other stoichiometry. It is just the same sort of 4 steps that we've talked about before. Difference being somewhere there, you're going to use the ideal gas law. So here we use it at the end. So step number 1, balance the equation. Step number 2, convert the moles. Step number 3, use the mole-to-mole relationship. And step number 4, convert those moles into something else. So again, very much the exact same steps, just inserting that ideal gas law into this. Any questions on any of those steps there? All right, let's see. Why don't you try one here? It's actually an experiment we're going to do next week, I think. Magnesium reacts with hydrochloric acid and hydrogen gas is produced. Calculate the volume of hydrogen gas produced at STP if 5 grams of magnesium reacts with excess hydrochloric acid, 2431 on magnesium there. You could look here. So we're looking to calculate the volume of hydrogen gas at STP. So once again, that is a temperature of 273 Kelvin. That is a pressure of 1 atmosphere. So we can think about PV equals nRT here for hydrogen. And we're obviously looking for the volume here. We do have the pressure given to us. We do have the temperature given to us. We do have R always. So once again, we are missing the moles there for hydrogen gas, which we can use stoichiometry to get us there. We're reacting 5 grams of magnesium with excess HCl. So obviously it's a basic stoichiometry problem, as it tells us this is really our limiting reagent. So in this case, we do have the equation is balanced. So the next thing we're going to do then is take what they gave us, which was 5 grams of magnesium, and convert it into moles. So we'll use the molar mass here, magnesium from the periodic table. And that will give us 5 divided by 2431, 0.2057, we'll call it, moles of magnesium. Once again, though, we are interested in hydrogen, not magnesium. So we do want to do the stoichiometry part here, which looks like it's not too bad. It is a 1-to-1 relationship. So that means 0.2057 moles of magnesium. Doing the stoichiometry here, 1 mole of H2 gives us 1 mole of magnesium, giving us 0.2057 moles of hydrogen in this case. So using our sort of stoichiometry here, we got ourselves 2 moles of hydrogen, which is the last thing that we need here. And we could use the ideal gas law to solve for volume in this case, which would be nRT over P. And that would be our 0.2057 moles, our gas constant, our temperature, which is 273 Kelvin, all divided by there, our pressure of 1 atmosphere. taking that there 0.2057 times 0.08206 times a 273 gets us about 4.61 liters as our volume that we would collect. Any questions on that there? Now, an alternative to this that you could have done was, because we were at STP in this particular case, we once again could have used 1 mole is 22.414 liters. And that means we could have just picked up from here and went with 0.2057 moles of H2, 22.414 liters per mole. And we would end up with the same thing. So again, you did not necessarily have to use the ideal gas law here because we were at STP conditions. But once again, you can see you get the same answer regardless of which way you go here. And again, we could only do it in this particular case because we were at STP conditions. Any questions on that there? Or gas stoichiometry in general? So like I said, gas stoichiometry, pretty straightforward, same steps. You could, again, like we talked about with solution stoichiometry, you could have a limiting reagent situation happening. So, you want to keep that in mind. But most commonly, one of the two places you will use the ideal gas law, either up front to figure out moles and then do the stoichiometry part of the calculation, or like we did in these couple here at the end, sort of use the ideal gas law and solve for something like volume. Any questions? All right, then the next thing we're going to talk about is the idea of Dalton's law of partial pressures, which sounds very complicated. So oftentimes when we have gases, they do come to us sort of as a mixture of different gases. So for example, if we had a container like we see kind of below, where we maybe just have red gas molecules moving around, and say these were all gas molecule A, for example, the total pressure here would be all result basically of gas molecule A flying around in there. And obviously, if we had a container that had, say, gas molecule B flying around, the total pressure would be all result basically of the second gas that's flying around in that container. If we put these guys together, where we have A and B kind of flying around in the same container, now the pressure, or the total pressure here, is a result of really both gases, the pressure of gas A plus the pressure of gas B. And these are what are referred to as partial pressures, because they partially contribute basically to the overall pressure of the container. By the way, in a laboratory situation, your total pressure is your barometer reading. Typically what that is. In a book problem, a lot of times they will give you the total pressure, but in the lab, it would be obviously the barometer reading. So a partial pressure is basically the contribution of that gas to the total pressure of that mixture. Now, one of the situations, or one of the things that makes something an ideal gas, which is sort of what we've been talking about up to this point, one thing that makes something an ideal gas is the idea that there is no sort of attractive forces or repulsion type forces between different gas molecules. And what that means is, although we may have in a container several different gases flying around, we can treat them like they were essentially in that container by themselves. And that's sort of the ideal situation. So even though there's multiple gases flying around, we could almost just treat them as, they're in there by themselves. And no interaction is going to happen between the different gases that are in the same container. So one of the most common ways that you could calculate a partial pressure is to actually just use the ideal gas law, PV equals nRT, and solve it for each gas. Like gas A, for example, would be nRT over V. And you could do it, say, for my example, gas B, which would be nRT over V. And basically what you would do is two separate calculations in this example here. where you would find the partial pressure of A and the partial pressure of B. And then to find the total pressure, you frankly just add them together, basically, is how you get the total pressure in that case. The good news is that because they're in the same container, the temperature in both cases are going to be the same because they're sitting in the same container in the same room. That also means that the volume for both of those guys will be the same as well because they're sitting in the same container. And obviously R is a constant, which typically means when you have sort of a partial pressure problem, the only thing you really need to calculate for the most part is the moles of each of the gases will be the different numbers. Everything else will be the same for everybody. And just to figure out the moles of each of those guys. So as I mentioned here, that is essentially what we can do. Now, in a situation where perhaps we don't have enough information to sort of calculate or use the ideal gas law, but maybe you have enough information to figure out the moles of each gas that are in there. You can also still figure out partial pressures if you know something like the total pressure, or if you know one of the partial pressures of somebody. And we could use something that we saw in the previous chapter, which is our mole fraction. So this is our mole fraction that we saw in the previous chapter, I believe. The mole fraction really is, again, the moles of what you're interested in divided by the total moles. And we could use the mole fraction and this equation in a situation where we don't really have enough information to go into the ideal gas law. This is the partial pressure of a gas. This is the total pressure. And this is obviously the mole fraction. So that's a very useful sort of equation. Again, in a situation where you do have enough to get to moles, but maybe don't have enough information to complete the ideal gas law. This allows you to actually solve it as long as you have enough of the information to do so. Any questions on that there? And if you remember, the mole fraction is kind of like a percentage without the multiplying by 100. So it's kind of converted into a decimal for you. So it's really the percentage times the total pressure will give you what the partial pressure is being contributed by that particular gas. So let's try some here, see what we got. All right, so why don't you give this a go. 5 grams of helium is added to 5 grams of neon in a 2.5 liter container at 27 degrees. What is the partial pressure of each gas and the total pressure here? So 3 answers, partial pressure of each gas and the total pressure of that mixture. Helium is 4.003 grams per mole. And who's our other guy there? Neon, 2018, I believe. All right. So partial pressure of helium. Okay, let's take a look and sort of see how we're doing. So we're looking for partial pressures of a couple of gases here. So obviously we have a mixture of both of these guys flying around in the same container. The good news about that is the volume for both of them will be the same. The temperature will be the same. So if we think about PV equals nRT, we do have the volume, we do have the temperature, we always have R. And in this case, we do have grams of each of them, which will allow us to get to moles. So we can solve for the pressure for each of them separately. So that's where we want to start, is to convert our grams into moles. So 5 grams of helium, using our molar mass here of helium, 4.003 grams per mole. And we'll do the same thing here for neon as well. 2018 grams per mole. That gives us for helium in terms of moles 4.003, which would be, we'll call it 1.25 moles of helium, and look like 0.248 moles of neon. That's really going to be the only difference between the two calculations, is the moles of each of these guys. So we will start with the partial pressure here of helium, which would be nRT divided by V. using the ideal gas law here. So putting in the moles of helium, 1.25, and our gas constant, and our temperature converted to Kelvin. So added 273 to that guy, I think is 300 Kelvin, all divided by our volume here of 2.5 liters. So that gives us 0.08206 times 300 times 1.25 divided by a 2.5 gives us a 12.3 atmospheres. That would represent the partial pressure of helium in this mixture. We're going to do pretty much the identical calculation here for neon. Once again, really the only difference here is going to be our moles, which will be 0.248 moles. Everything else is going to be the same since they're in the same container. And in this case here, gets us a 2.44 atmospheres. And that would be considered the partial pressure of neon here. Any questions up to there? At this point, to get to the total pressure, we're going to basically just add them together. So total pressure be the partial pressure of helium plus the partial pressure of neon, which gives us 12.3 atmospheres plus a 2.44 atmospheres. Going to give us like a 14 something 7 maybe. 14.7 atmospheres being our total pressure in this case. Any questions on any of those steps here? The major contributor here to the pressure of this mixture is which gas? It is the helium. And any ideas why that might be? We're going to talk about it in just a second, but it is because helium is much lighter. So a much lighter gas going to be traveling a lot faster, going to result in more collisions than what we see with neon in this particular case. Any questions on any of that there? Okay. All right, so why don't you give this one a go? A sample natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane, that is, I believe. If the total pressure of the gases is 1.37, what is the partial pressure? In this particular case, we got some moles of everybody here. So we got 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane here. And we do have the total pressure given to us, which is 1.37 atmospheres. And we're looking for the partial pressure here of propane. So in this case, we really aren't given any temperatures or volumes and stuff like that. So really the ideal gas law is not going to help us too much here. So we can use that other equation that we saw, which is this guy here. Partial pressure is equal to the mole fraction times the total pressure. That would mean we would want to figure out the mole fraction of what we're interested in, which was propane in this case. So to figure out the mole fraction, once again, we take the moles of what we're interested in and we divide it by the total moles here, which would be adding all those guys together. And that's going to give us a mole fraction of it's like 0.0132. We already have the total pressure, so our partial pressure here then of propane would equal our 0.0132 times our 1.37 atmospheres, which is our total pressure, and gives us approximately, we'll call it 0.081. Whoops, there's a 1 in there. 0.0181 atmospheres. There we go. Any questions on that one? So again, this one's useful, like we can see here, if we have just moles, or maybe we just have grams given to us and not moles, but we can convert it into moles by using the molar mass. And again, really you just need one of these two things that allow you to use this equation, either the total pressure or a partial pressure of somebody that's there, and you can pretty much use this equation. Any questions on that one there? We obviously could do the partial pressures there for everybody else the same way. All right, so this again is another sort of example of partial pressures. A very common situation where we do end up with partial pressures is a very common sort of lab practice where we collect the water, or collect the gas, and it's how we collect the gas. So for example, if we did this experiment, which is some potassium chlorate here, and we start heating it up. As we start heating it up, we're going to make some oxygen gas, which is in this tube. It has nowhere to go. And usually the gas will come into a collection beaker or container that's filled with water. So as the gas comes in, the water escapes out. The result of that is the gas here is collected up in the empty spot, which is really not empty, but it has actually the gas in it. And in this case, this is where, in this particular example, the oxygen gas would actually enter as well. But just by sort of a side effect of collecting the gas this way, where we collect it, where water is involved, water and some reaction is going to generate some heat and stuff like that. Heat and water will also create in here some water vapor. So just as a result of sort of the way that the gas was collected, is sometimes referred to as collecting it over water, or sometimes referred to as being saturated with water vapor. But any process where you collect a gas where essentially you displace water out of the container and allow the gas to come in is usually a situation where you will end up like this. Now, the deal is you get both of those gases for the same low price, but the interest of what you are interested in is actually just the actual gas you're looking at, which would be the oxygen gas. So in this situation, we do get a mixture of the gas you're interested in and the water vapor. So we oftentimes have to do sort of a correction where the total pressure in this case would be the pressure of the gas you're interested in, plus the vapor pressure of water, which, by the way, is typically a value that you can look up in a table based on the temperature of the water and so forth. So we do want to, if we were going to continue on, for example, and do some calculations, or if we just wanted the pressure of the gas that we collected, we would have to do this sort of correction, which means that the pressure of the gas we're interested in would be the total pressure, which is the barometer reading, minus the vapor pressure of water. So basically we need to subtract off the water's contribution here to the pressure. And sometimes it's referred to as getting the pressure of the dry gas, because you kind of subtracted off the water part of it. So anytime you collect a gas in this manner, and in a book type of problem, it will say something like it was collected over water. Like I said, it was saturated with water vapor. That is pretty much this type of situation where, it's not too bad. It's kind of a subtraction problem in a lot of cases. You basically will just subtract off the contribution of water. And again, this is the vapor pressure of water, which is what you could look up in a table in most cases. So let's take a look at one here. Here's a table of the vapor pressure of water, again, similar to one you can look up. And again, it's based off of temperature. And you just kind of find the correct value. So a sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824. What is the partial pressure of the oxygen gas? So this is a situation like we just saw in that picture. We're collecting the water, the gas over water, and we know that by this sort of term there, saturated with water vapor, sort of tells us that it is that situation. So in this case, the total pressure would be the pressure of the gas we're interested in, which is the oxygen gas, plus the vapor pressure of water. In this case, they did give us the total pressure, which was 753 torr. The pressure of the oxygen is what we're interested in. And this is a table value, which is where that value comes from. So they looked it up in the table at 30 degrees Celsius, and the vapor pressure of water is 31.824 torr in this case. That means our partial pressure here really of oxygen is 753 torr minus 31.824, or gets us 753 minus 31.824, gives us about a 721 torr. We do want it in atmospheres, so we want to do a conversion. 721 torr. Again, that is our 760 number there. We'll convert it into an atmosphere. And it looks like 0.949 atmospheres would work here. So this is sort of a third sort of partial pressure situation that occurs very, very commonly in the lab. And you do have to sort of subtract off the contribution of water. And the good news is it's not too hard of a partial pressure problem. A lot of times just adding or subtracting. You could be given a partial pressure as well and figuring out the total pressure and stuff like that. Any questions on that one there? Okay. So we're going to talk a little bit about kinetic molecular theory of gases here, and some of it which we've talked a little bit about up to this point. So first off, a gas is composed of molecules that are separated by distances that's greater to their own. So we consider these molecules to be points, and they possess a negligible volume. So this is really one of the things that makes something an ideal gas, is the idea that they have a negligible volume, or really the volume is not that important compared to the container. So if you look back at a lot of problems that you do when you're dealing with gas laws and gas problems, a lot of times what they will talk about is the volume of the container itself rather than the volume of the gas, because the volume of the container is much larger, much more comparable than the small little gas molecules that are flying around. And since in an ideal situation, they're filling it uniformly, we consider sort of the volume of the container basically the same as a gas. So that is one thing that makes something an ideal gas, is that situation right there. Gas molecules obviously are in constant motion. It is the collisions that occur. The collisions among molecules are perfectly elastic. The collisions is what causes the pressure, but they are perfectly bouncing off of each other. They're not really affected by the other guys that are there. And that way, you know, there's no sort of effect on the total pressure as they are bouncing around in there. The third thing here is the second thing that really does make something an ideal gas, is this idea here that gas molecules will neither exert any attractive forces or repulsive forces to one another. Again, with the idea that, you know, they're bouncing around, they're just kind of bouncing around perfectly off of each other, not really affecting each other. Again, this is why what we just did in the partial pressure situation, we could do this way, because in an ideal situation, even though there's multiple gases in the same, say, container, they're really having no effect on each other. So again, it's like they're there by themselves. They were not affected by any type of attracted or repulsive forces. We'll talk a little bit about it later on in this chapter at the end when we talk about real gases. But, you know, if we did have some type of gas molecule that was attracted, for example, to the guy behind him, that would kind of slow him down as he moves into, say, the wall and so forth, and collisions, and that would affect obviously the pressure that would happen if there was this sort of attractive force, or even if there was a repulsive force where they wanted to get away from each other, it would cause some differences in the pressure that you would associate with it. But in an ideal situation, the gas molecule's volume is not important, it's zero, and basically there's no attracted or repulsive forces between different gas molecules. The average kinetic energy of molecules is proportional to the temperature of the gas in Kelvin. So sort of the idea we talked about, as we increase the temperature, we would expect the gas molecules to fly a lot faster and move around a lot faster. And obviously, as we lower the temperature, they would have less energy and would fly around not as fast and move around as fast. And we saw that with some of the laws that we talked about. So our Boyle's law, again, is proportional. The pressure is proportional to the collisions with the wall of the container. And again, as one goes up, one comes down, as we talked about with that, pressure goes up, volume comes down, and vice versa. Obviously, smaller volume, less room for everybody to fly around in, causing a lot more collisions. Charles' law, again, is related to sort of temperature as well. So if we increase the temperature, we will need the volume to adjust to allow the pressure to remain constant. And if we decrease the temperature, we need that volume to adjust to maintain the constant pressure. In a constant volume situation, we will definitely see the effect as we see here. As we increase the temperature, so does the pressure. And as we decrease the temperature, the pressure would drop down as well. Avogadro and our number of moles. Again, the number of moles is proportional to the pressure. So obviously more gas molecules, more moles of gas molecules, we would expect more collisions and more pressure. And again, the sort of idea that there is no attractor repulsive forces there with our partial pressure situations means that we could treat each gas individually by themselves, and they're not affected by other gases that are there. Any questions on that there? So speaking a little bit about this, we're going to talk about sort of how we can figure out how fast, for example, gas molecules are moving. And there's an apparatus such as this here to study it with some spinning wheels as they detect, and the faster molecules hit it, kind of slower molecules all kind of combine together. And that brings us to what we see here in a couple of these graphs. So up here on the top left, we have nitrogen at some different temperatures. So this is all nitrogen gas, and this is the speed and the number of molecules. So we can see at 100 Kelvin, basically this bunch of molecules have about that much speed. When we increase it to about 300 Kelvin, about that much, guys, do you see the speed starts to increase? And when we hit it to 700 Kelvin, we got a greater proportion of molecules that have more energy, and we see that the speed starts to increase. So what we see here in terms of nitrogen, the same gas at 3 different temperatures, is we do see that the speed of the gas does start to increase as it picks on more temperature. When we look at different gases at the same temperature, so this is all the same temperature at 300 Kelvin, this is chlorine, nitrogen, and helium. We see that chlorine here basically has this speed. We see nitrogen is basically this speed, and we see that basically helium is over here. What we actually see here is helium is the fastest in terms of its speed versus nitrogen and versus chlorine. The difference is as we go this way in terms of the things there, it gets heavier. So as the molar mass of the gas increases, they're going to be heavier. They're not going to be able to fly around as fast, or they're going to have a lower sort of speed as compared to the light guy, which is helium here, which would have a much larger speed. We could calculate the speed of a gas by calculating this, which is what is referred to as the RMS. That is the root mean square velocity. And it is in meters per second is typically what we calculate it in. So the root mean square velocity here is equal to the square root of R times the temperature divided by the molar mass here. Now, when we use this equation, a couple of things are different. The R value here is actually 8.314 joules per Kelvin per mole. So this R value is the really energy version of R. The temperature here is in Kelvin. And the molar mass, which is this bottom guy, that's the molar mass, actually needs to be in kilograms per mole, not grams per mole. So when you use this equation, you have to have it in kilograms per mole and not grams per mole, and it has to do with the R value here. If we remember, I think we saw this in an earlier equation, but if you remember, a joule is equal to a kilogram meter squared second squared. And that basically means that we need that guy's unit there to be kilograms on the bottom, so everything cancels out. So if we look at this here, find somewhere to write there. I'll do it here. Yeah. So so if we look at that equation, which is the root mean square is equal to square root of 3RT over M. If we just look at the units here, 3R would then be kilograms meter squared second squared, Kelvin and mole. Temperature would be Kelvin, and we would do our molar mass in kilograms per mole. The kelvins will cancel, the moles will cancel, the kilograms will cancel. That basically leaves us the square root of meter squared over second squared, which when we take the square root of it will leave us with meters per second in terms of the units here. And the good news is R is still the same number, regardless if you use it as joules or whatever, the number doesn't say, so it's still 8.314. The only real important part is the bottom part there. Instead of grams per mole for molar mass, you do need to get it into kilograms per mole so that all the units does cancel out correctly. So I think what we'll do is we will lay it up there and we'll finish this up tomorrow, I think.